In this video, we're going to continue looking at problems that deal with the fundamental theorem of calculus part 1, also referred to as the do-nothing theorem. All right. So for this first problem, we are given g of w is equal to the integral from 0 to w of sine evaluated at 9 plus t to the power 7 dt. So it's important to determine which case you're in. And here we are in this first case where we are integrating from a constant to a variable. This is the easy case. All we need to do here is just replace the variables. So g prime of w is equal to sine of 9 plus w raised to the power 7. Like I said, that's all that there's to it in this case. In the second case, next problem, we would like to find the derivative of h of x. And here h of x is given as the integral from 1 to the square root of x for a function z squared divided by z to the power 4 plus 5 dz. Now, before I jump in, let me quickly just give a reminder. In Calculus 1, we learned not a shortcut, but we formalized the derivative. If we ever need to find the derivative of the square root of x, remember that if you clean this up, so really we're finding the derivative of x to the power 1/2, right? So using that power rule, this will be 1/2 x raised to the power -1/2. Or a better way to write this would be 1 over 2 times the square root of x. So we pretty much formalized this. I will be referring to the derivative of the square root of x as 1 over 2 times the square root of x, and I will not be reducing it each time in this way. So this is worth putting on one of your little cards that you're going to memorize. All right, so on to our problem then. H prime of x. And again, maybe before I jump in, I think we need to identify that here we are in case 3. So this is a case where we are integrating from a constant to not a variable, but a function. The square root of x is a function, right? So we're going to plug in the top times derivative of the top. So this will be the square root of x squared over the square root of x raised to the power 4 plus 5. So plug in the top and then times derivative of the top. And again, we just said the derivative of the square root of x is 1 over 2 times the square root of x. I would like to clean up my expression just really ever so slightly. We can write this, of course, the square root of x squared is just going to be x over x squared plus 5 times 1 over 2 times the square root of x. I'm going to keep this in parentheses just to make sure we see that these two terms are being multiplied together. All right, in the third case, we are given f of x equal to the integral from x to x squared of e to the t squared dt. Now for this problem, and I'm just going to kind of scroll down here for a second so you can see, we are going to be in case 4. So this is the case, and really a generic case for all of the others, where we are finding the derivative of an integral, but the bounds here go from one function to another function. And so if we kind of want to formalize this, what we're going to do is plug in the top times derivative of the top minus plug in the bottom times derivative of the bottom. So here we go. Remember good notation, f prime of x is equal to, all right, I'm going to start by plugging in the top. So this will be e raised to the, I'm going to replace the t with an x squared. So e to my variable squared, or in this case, my function is going to get plugged in. So plug in the top times derivative of the top. So that is, what is the derivative of the x squared that I just plugged in? That will be 2x minus, now we're going to plug in the bottom. So this will be e to the x squared times, again, the derivative of what you just plugged in. Derivative of x is equal to 1. And again, if you wish to clean this up, we could write this as e raised to the x to the 4th times 2x minus e to the x squared. All right, another problem here from 5.3 wants us to evaluate an integral, but the function given here is a piecewise function. So first, I will remind you of the properties of integration that says that the integral from a to b of f of x dx plus the integral from b to c for the same function f of x dx can be given as the integral from a to c. Right? So since this is a piecewise function, we will be breaking up the integral into two parts. So we will be finding the integral from 0 to pi, and we're going to add that to the integral, the integral from not to pi, but to, of course, to pi halves. We're breaking it up at pi halves. And then we will add the integral from pi halves to pi. So on the integral from 0 to pi halves, the function that the problem says to use is sine of x. And so we will add to that the integral from pi halves to pi of, on that interval, we're using the equation cosine of x. So let's integrate. The integral of sine of x is equal to negative cosine of x. And we are going to evaluate from 0 to pi halves. All right, I'll kind of put these in parentheses. Plus, and the second component here, the integral of cosine of x, of course, is equal to sine of x. And we're going to evaluate from pi halves to pi. All right, so now using that other fundamental theorem of calculus, we will plug in top minus plug in bottom for both of these. So I will have minus cosine of pi halves minus negative cosine of 0, plug in top minus plug in bottom, plus, again, the other component here, plug in top minus plug in bottom, sine of pi halves. If you forget the values of sine and cosine at these sort of common angles, I included a graph to remind you. We know that cosine evaluated at pi halves is equal to 0, minus cosine evaluated at 0 is equal to 1, but this is a negative function, so this will be negative 1, plus sine evaluated at pi, we can see here that's equal to 0, minus sine evaluated at pi halves is equal to 1. And again, when we simplify here, we get 1. Let's see, minus negative 1, that's equal to going to be positive 1 minus 1. This is equal to 0. And again, just to confirm here, let's look back at our graph and make sure that graphically this does make sense. I'm going to go ahead and shade on my graph here for you. The integral of sine between 0 and pi halves, so if we shade the area under sine between 0 and pi halves, this is the little area that we're looking at, right? And then if we shade the area under the graph for cosine, well, between the x-axis and cosine on the interval from pi halves to pi, then we're looking at this little area right here. And so you can see immediately that since these two areas are symmetrical in nature, but one of them is above the x-axis, the other one is below, of course, these areas will cancel out. It's that net area problem, which confirms graphically to me that my answer here should be 0.